Hi everyone, my name is Natarajan. I worked on this project as a high school student over the summer of 2019 at Stanford University. I'm currently a freshman at UC Berkeley studying computer science. In this project, I developed computational methods to analyze the progression of tracer through the brain using MRI images acquired before and after ultrasonic manipulation of the glymphatic system. Currently, our image analysis pipeline uses software such as Osirix, which is effective but requires manual delineation of the regions of interest, which is prone to error and is very tedious. Our proposed solution is a novel analysis pipeline that will automate this process. The user will simply input a large group of DICOM files and receive an analysis of the change in intensity and change in volume over time without any further manual input. This is significant because automated post-processing of the imaging data will rapidly speed up and simplify analysis to allow researchers to focus on optimizing their experimental preparations. So, onto the program. The first step is registration. We have to organize the folder of DICOM files, split them up by time and sequence, and then crop them. So each DICOM file contains a bunch of information. Important features to note include image type, series time, series description, and image position. I use these features to organize the data. So if you go through each DICOM file and display the image, you'll notice that each slice has 5 corresponding images. You can see in this plot that each row corresponds to the same image position. So the program has to automatically select the correct image out of the 5 to use. And I found that selecting the one with the highest mean does the trick. After the initial filter, we now sort by series time and we get 9 different series times, as you can see on the left, for this particular data set. Each time has a total of 9 slices at different z-values of the brain, but I'll go over that in a little bit. Each time has a corresponding series description which tells us the sequence, as you can see on the right, and we only want to use the sequences that are titled parametric image for T1 saturation recovery for our analysis. So in this case, it's the 2nd, 4th, and 6th sequences, so we'll have 3 different time points to compare. Each sequence type will give us a different data, so we need to be sure to select only the correct sequences. Before I move on to the next slide, I want to point out that in these images, you can see more than just the brain. You can see the full head and the eyeballs, and we don't want that to influence our decision. So you have to crop the scans. These 9 images are the scans for the different slice locations at one particular time point. The top left shows you the bottom of the brain, and it goes up until the top of the brain on the bottom right. So these are the different z-values. As I mentioned before, we have 3 time points, so in total we have 27 scans for this data set. Just to note, in the beginning, we had over 400 scans before we did any registration of the data. Filtering it down to these 27 scans and cropping is all automatic. Now that we have our data registered, we're ready for analysis. We first have to normalize the scans, then find a baseline value, and finally extract the intensity and volume at each time point. To normalize the values, I converted each pixel to its z-score for the entire time point, so all time scans from one point are normalized together. Then I multiplied the values by the mean so that values aren't too small and close together. In these plots, you can see the effect of the normalization. For actually calculating the intensity and volume over time, I set the baseline statistic by using the t-value of the first time point and 95% significance. I then summed the pixel values above that statistic at each time point for the intensity and multiplied them by the slice thickness for the volume. In the end, plotting the data from our 3 time points gives us these graphs. This decreasing intensity and volume makes sense for this data set because we're tracking the progression of tracer through the glymphatic system. At the beginning, there should be a lot because it was just injected, and as time goes on, if everything is working properly, it should leave the brain. Here are some plots that show you how the program works. On the bottom row, the highlighted points that are the points that are deemed above the baseline statistic in the normalized scan. So those are the points that are added to calculate the total intensity. There are still some challenges with this program. These 2 scans above are from the same sequence but are a part of different data sets, meaning that they were taken on different days. Because of this, there is a small movement in the location of the brain. This makes cropping extremely difficult because we can no longer apply one cropping mask for each sequence. To fix this, I tried to subtract the scan from itself, offset by 1 pixel, and I got the scan on the left. You can roughly see the outline of the edges, but it's not clean enough to perform an exact crop. I then made a machine learning model to outline the edges, but we still have the same problem. Visually, it makes sense, but it's very messy. So for now, this program works on most datasets, but still has trouble with some. I'd like to thank Dr. Mona Ariel, who is my mentor for this project and is also presenting here, and Dr. Iron in the Iron Lab for letting me intern over the summer. I'd also like to thank the Focus Ultrasound Foundation for awarding me with the Global Internship Stipend for this project. Thank you very much.